Hi, my name is Gaia Bacon. My project is about the impact of lossy image compression on astronomical magnitude measurements. I am from North Carolina School of Science and Math at Durham, and I'm in the M3 program. I've been working on this project with the support of my mentor, Dr. Arun Kanavati Jayaraman at Duke University. Every night, observatories collect terabytes of image data, and managing this huge amount of data is challenging. So, astronomers use lossy compression to reduce file size. And while this saves space and speeds up transfers, it permanently loses some of its data. This raises the question, how much compression can we apply before losing scientifically important information? One key value that could be affected is magnitude, which shows how bright an object appears to us. Astronomers depend on magnitude to understand properties of objects like stars and galaxies, such as distance and size. And even small errors in magnitude can cause huge misinterpretations, which is why it's important to study how compression impacts magnitude. My research will ask the question, at what point does lossy compression start to change the magnitude measurements in astronomical images? And when do the differences in mag-auto values stay within our ideal range of plus or minus 0.001? My main goals in this project will be to compare magnitude values from compressed and uncompressed images, identify the compression level where magnitude becomes reliable, and determine the trends and patterns of lossy compression. This is the image that I used for my experiment. I used this file and compressed it with using various different compression levels from 0.3 to 800. After compression, I decompressed the file so I could extract data from the image, like measurements of magnitude. At first, we noticed that some of the more compressed images miss some objects. And to fix this, we used a method called double image mode, which uses the object's position from the uncompressed image to find and measure those same objects in the compressed image. As seen in the images on the right, the version without using double image mode shows much larger differences in mag-auto than the version with double image mode. This confirms that double image mode significantly improves our measurement consistency. Then I compare the brightness values called mag-auto between the compressed and the uncompressed image. We focus on the differences within our ideal range. Finally, we create a plot showing how the brightness difference and the file size change with our various different levels of compression. Now, the first compression level where this acceptable mag-auto difference range was met occurred at a Q level value of 1,000, where Q just represents the strength of our compression. This comparison graph shows that at Q equal 1,000, 99.6% of objects have a magnitude difference within our acceptable range. Another notable result is visible in the graph next to it. Galaxies, shown in red, displays much more significant distortion and larger difference in mag-auto compared to stars, which was shown in blue. Now, this slide highlights some trends that we observed. As the Q value increases, so does the file size and the number of detected objects. Eventually, the number of detected objects matches that of the uncompressed image. Along with this, as file size increases, the average mag-auto difference gets closer and closer to zero. And the standard deviation of mag-auto differences also decreases and comes closer and closer to zero. This shows how the differences were less spread out at larger Q values. In conclusion, lossy compression can be applied safely at a certain point. Before that, magnitude measurements were unreliable, particularly for fainter objects. Knowing that threshold helps balance efficiency with scientific reliability. These findings can guide astronomers working with large datasets like those from LSST or Roman. Compression settings can be chosen to preserve scientific quality without unnecessary storage costs. And future research in this area can explore why faint and bright objects, or rather stars and galaxies, responded differently to compression. And it could also include research on how measurements other than magnitude are affected by lossy compression. Understanding these patterns and trends can lead to more effective compression techniques that will reduce file size while still preserving critical scientific information. Now, I would like to thank my mentor, Dr. Arun Kanavati Jayaraman, and as well as Dr. Lena Sarcevic and Dr. Lauren Alderete. I would like to thank the Duke Cosmology Group and North Carolina School of Science and Mathematics Mentorship Program for helping me through this process. And I would like to thank the Boris Wellcome Fund and NCSM Foundation for making this experience possible. Thank you.